About 13.8 billion years ago, according to the Big Bang theory, everything we know started from a point unimaginably small and dense. But have you ever wondered what was before that? In the 1980s, the concept of inflation added a twist to this narrative. It suggests that the universe underwent a period of extremely rapid expansion almost immediately after the Big Bang. This theory has reshaped our understanding, but it also opens new questions, like what triggered this inflation? What was before that? Now, applying Einstein's general theory of relativity, which connects gravity to the curvature of space-time, researchers are pushing the boundaries even further. They are exploring scenarios that extend back to times preceding the Big Bang. Yes, we're talking about looking back beyond the very beginning of everything. Recently, a team of mathematicians proposed some fascinating ideas. They suggested that the singularity, the point where traditional physics breaks down, and where the Big Bang supposedly started, might actually be an illusion. Imagine that. What if the start of our universe wasn't a singular point at all? These are not just mathematical speculations, they challenge our understanding of the cosmos and could redefine the science of cosmology. So, what do you think was before the Big Bang? An endless loop, another universe, or perhaps something we haven't even imagined yet? Theories abound, but for now the mystery remains tantalizingly out of reach. Mathematics is often described as the language of the universe, and it provides a powerful framework for understanding the physical world around us. Here's how mathematics explains the universe. First, let's talk about math as a universal language. Mathematics allows us to describe patterns, structures, and relationships in a precise and consistent way. This universality makes it an essential tool in physics and cosmology. Next, consider how mathematics helps in describing physical laws. The laws of physics, which govern everything from the motion of planets to the behavior of subatomic particles, are expressed in mathematical terms. For example, Newton's law of universal gravitation can be written as F(g)(2r², where F is the force of gravity, g is the gravitational constant, m1 and m2 are the masses, and r is the distance between the centers of the two masses. But it doesn't stop there. The predictive power of mathematics is truly astounding. Mathematics enables predictions about the universe. For instance, the existence of the planet Neptune and the Higgs boson particle were predicted using mathematical equations before they were observed experimentally. Some physicists, like Max Tegmark, propose that the universe itself might be a mathematical structure. This means that all matter, including particles with properties like charge and spin, and even space itself with its dimensions, are ultimately mathematical constructs. We also see patterns in nature that suggest an underlying mathematical order to the natural world. For example, the Fibonacci sequence in the arrangement of leaves or the fractal patterns in snowflakes. Finally, in the realms of the very small and the very large, quantum physics and relativity provide mathematical descriptions that, while incredibly successful, also highlight the limits of our current understanding and the potential for new mathematics to reveal more about the universe. So, as we continue to explore the cosmos, let's remember that mathematics is not just a tool, but a universal language that helps us decode the mysteries of the universe. We've journeyed through the mysteries before the Big Bang and marveled at the language of the universe, mathematics. Now, let's dive into some of the most profound unsolved mathematical problems in cosmology. These puzzles challenge our understanding and push the boundaries of human knowledge. This is one of the most significant enigmas in theoretical physics. The cosmological constant, denoted by lambda, represents the energy density of space or vacuum energy. The issue arises because theoretical predictions for the value of lambda are vastly greater than what is observed. This discrepancy is often referred to as the worst theoretical prediction in the history of physics. In the context of the multiverse and eternal inflation, the measure problem concerns how to compute the ratios of different types of universes within a multiverse. Different methods yield different results, and there is no consensus on which approach is correct. This leaves us pondering the true nature of our cosmic neighborhood. While not purely mathematical, these hypothetical forms of matter and energy are invoked to explain observations that cannot be accounted for by known physics. Yet their fundamental nature remains a mystery, eluding even the most advanced mathematical models. This problem relates to the uniformity of the cosmic microwave background radiation. The universe appears to be isotropic, meaning it looks the same in all directions. This is puzzling because regions of the universe have not had enough time to exchange information or energy to reach this uniform state. The universe appears to be flat, meaning the geometry of space is Euclidean. However, the reason for this observed flatness, given that various cosmological models predict different geometries, is not well understood. Why does our universe defy these predictions? General relativity predicts singularities, points where the curvature of space-time becomes infinite, such as at the beginning of the universe, the Big Bang, and at the centers of black holes. The physical meaning of these singularities and how to reconcile them with quantum mechanics is an open question. These unsolved mathematical problems in cosmology are more than just academic exercises. They represent the frontiers of human understanding, urging us to continue our quest for knowledge. Each mystery holds the promise of new discoveries and deeper insights into the very fabric of reality. In our previous scene, we delved into the unsolved mathematical mysteries in cosmology, with the cosmological constant problem taking center stage. Now, let's explore some of the proposed solutions to this profound enigma. First, we have the approach. This solution involves adjusting the parameters of the theory to match observations. However, this requires an incredibly precise adjustment, which many physicists find unsatisfactory due to the lack of an underlying principle that explains why such fine-tuning should occur. This principle suggests that the universe must be compatible with the conscious life that observes it. Therefore, the cosmological constant is what it is, because if it were significantly different, the universe would not support the development of life. Quintessence is a hypothetical form of dark energy with a dynamic equation of state. Unlike the cosmological constant, which is constant, quintessence changes over time and could potentially explain why the cosmological constant is so small. String theory proposes a vast number of possible universes, each with its own set of physical laws. The cosmological constant problem might be solved statistically in this landscape, with our universe being one where the constant happens to take on a small value. These theories suggest modifying general relativity at cosmological scales. These modifications could potentially counteract the effects of vacuum energy and lead to a small observed cosmological constant. Present yet another intriguing possibility. These models suggest that we live in a large void, and the apparent acceleration of the universe's expansion is due to the difference in gravitational pull between the void and the denser regions outside it. Lastly, in this scenario, dark energy decays over time, which could lead to a small value of the cosmological constant in the present era. These proposed solutions to the cosmological constant problem showcase the creativity and ingenuity of the scientific community. Each solution offers a unique perspective and brings us one step closer to unraveling this cosmic mystery.